So far we have just looked at a vector quantity as something that has a direction and that has a magnitude. But now we are going to look at some more properties, and one property that we specifically look at is the change of vector components under rotation. Let us see that. Suppose you have a friend who asks you how far is the house of another friend, and you say it is 500 meters, or you say you walk 300 meters to the east, I am just taking the previous example, and 400 meters to the north. So that the direct distance of that house is 500 meters, but you have to walk in a zigzag manner, in that you have to go east first and then north. Total distance you cover is 700 meters. Now, suppose you have another friend who is looking at it from a different frame. So, for the previous friend you had the x axis along the east and y axis along the north, but another friend has his axis x prime, and this at some angle theta from the east and y prime at some angle theta from the north. Although the distance travelled by this person in going to the other house is going to be 700 meters in both the frames. However, this vector you can see is going to have components which are not going to be 300 and 400 meters, but this is going to be its x component and this is going to be its y component. So, although the vector remains the same, it is 500 meters in this northeast direction, but its components along different frames are different. On the other hand, for the scalar quantity distance, that remains the same, unchanged. So, what we conclude, a scalar quantity which is nothing but a number remains unchanged in the two frames. On the other hand, we also see that the components of a vector quantity change when we go from one frame, say x y, to another frame which is rotated with respect to the first frame, x prime y prime, which is rotated by an angle theta with respect to the first frame. For the same vector quantity, which in space is still pointing in the same direction, has the same magnitude, this is going to be x component, this is going to be y component. On the other hand, the x prime component is going to be this and y prime component is going to be this. And the relationship between x prime and y prime component and x and y component is well known, and that is what we are going to derive now. So, a vector quantity must follow that relationship, its components should change according to that relationship when we go from one frame to another frame which is rotated with respect to the first frame. So, let us derive the relationship. So, let us say there is a vector pointing in a certain direction in the original frame x and y, so that its this is its x component and this is its y component. I am looking at the same vector from another frame, and let me now use a different color. X prime and y prime frame, which is rotated with respect to the first frame by an angle theta. The component x prime is going to be given here. This is going to be x prime and this is going to be y prime. you can also see that this angle is also theta. Let me also draw a perpendicular from here to here. This angle is also theta. Let this point be A, B, C. This is the origin. Let this point be B prime. Let this point be C prime. So, we see that x prime component is going to be equal to O C prime plus C prime B prime, that is this plus this. And let me also call this point where it intersects as D. OC prime is nothing but x cosine theta. So, this is going to be x cosine of theta plus C prime B prime is nothing but C prime D plus D B prime. So, this is nothing but C prime D plus D B prime, which is equal to x cosine of theta. C prime D is nothing but D B sine of theta, D B sine of theta. I am deliberately writing it like this, plus D B prime is nothing but A D sine of theta. Sine of theta I have taken out. Now, you see D B plus A D is nothing but y. So, I can write this as x cosine of theta plus y sine of theta. And what I have shown you in the previous page is that x prime is x cosine of theta plus y sine of theta. Similarly, if I were to calculate y prime, this length, this, let me extend this here, this distance is nothing but, this angle is theta, y cosine of theta minus this distance, which is the same as this distance, which is nothing but x sine theta. So, y prime therefore, is going to be y cosine of theta minus x sine of theta, and this is how the x and y components of the vector are going to change. I wrote this for a displacement vector x and y, but in general you can do the same exercise and you would find that if I look at a vector A in the two frames, which are rotated with respect to each other, then A x prime, that is the component of A in the rotated frame, is going to be equal to A x cosine of theta plus A y sine of theta, and A y prime is going to be equal to minus A x sine of theta plus A y cosine of theta. This is how the components of a vector transform. On the other hand, the scalar number remains the same number in both the frames. We have looked at, in this case, when we rotated the frame about the z axis, because only x prime and y prime axis changed. We can do the same thing for other axes also. So, for example, suppose we rotate about the x axis. So, let us say we have x, which is coming out, y and z, and suppose we take the new frame by rotating about the x axis, x y and z x is the same. So, this is going to be y prime and this is going to be z prime by an angle theta. Then you can see that what we did earlier, by that a y prime in the rotated frame when I rotate about the x axis is going to be a y cosine of theta plus a z sine of theta, and a z prime is going to be equal to minus a y sine of theta plus a z cosine of theta. Similarly, if I rotate about the y axis, let us do that. If I rotate about the y axis, this is going to be x axis, z axis, y axis coming out, and make my new z prime and x prime axis like this. By rotating about the y axis, you will see that a z prime is going to be a z cosine of theta plus a y sine of theta, and a x prime is going to be minus a z sine of theta plus a y cosine of theta. So, this is how the vector components of a vector transform under rotation with respect to x axis, y axis or z axis. That is, if I rotate about the z axis, I change x prime and y prime components. If I rotate about the x axis, I change y and z components, and if I rotate about the y axis, I change x and z components, and they change in a very specific manner. On the other hand, the scalar quantity remains unchanged even if it is looked at from a rotated frame, and that we are going to use now to define our products. So, first quantity I told you about is of those, let me write all the components ax, bx, ax, by, ax, bz, ay, bx, ay, by, ay, bz, az, bx, az, by, az, bz. Of all these 9 components, we took 3 of them and wrote a scalar product as the sum of ax bx plus ay by plus az bz, and we call this a scalar product. That is, if I take these components and add them up, this gives me a number which is scalar. How do I prove it? I prove it by going to a new frame in which the scalar product is going to be ax prime bx prime plus ay prime by prime plus az prime bz prime, and this ax bx plus ay by plus az bz must be the same as ax prime bx prime plus ay prime by prime plus az prime bz prime if this is a scalar. Let us show that for one specific case, and rest I will leave for you as an exercise. So, let us look at the rotation about z axis. So, that in that case ax prime would be equal to ax cosine theta plus ay sin theta, bx prime would be similarly bx cosine theta plus by sin theta, ay prime would be minus ax sin theta plus ay cosine theta, by prime would be equal to minus bx sin theta plus by cosine of theta, A z prime would be same as A z, because z axis is not changing, I am rotating about the z axis. B z prime would be same as B z. Now, let us calculate A x prime B x prime plus A y prime B y prime plus A z prime B z prime, and this would come out to be equal to A x cosine theta plus A y sin theta times B x cosine theta plus B y sin theta plus minus A x sin theta plus A y cosine theta times minus B x sin theta plus B y cosine theta plus A z times B z. This gives you A x times B x cosine square theta plus A y times B y sin square theta. The first term gives you A x B x cosine square theta plus A x B y cosine theta sin theta plus A y B x cosine theta sin theta plus A y B y sin square theta plus A x B x cosine square theta minus A x B y cosine theta sin theta minus A y B x cosine theta sin theta plus A y B y cosine square theta plus A z B z. Now, you see this term cancels with this term cancels with this, and A x B x cosine square theta plus A x B x sin square theta gives me A x B x. Similarly, A y B y sin square theta plus A y B y cosine square theta gives me A y B y, plus last term is A z B z. So, what I showed you just now by transforming the different components, that A x prime B x prime plus A y prime B y prime plus A z prime B z prime, even under transformation remains the same as A x B x plus A y B y plus A z B z, and therefore, this is a scalar quantity, and that is precisely why we take this particular combination A x B x plus A y B y plus A z B z and call this a scalar product. Similarly, the other quantity that we define is the vector product, in which case A cross B is given as I, the x component is given as A y B z minus A z B y, plus the y component is given as A z B x minus A x B z, plus the z component is given as A x B y minus A y B x. What happens under transformation? Under transformation, if I transform each component A x, A y, B y the way we did earlier, these components should also mix according to the rule of vector transformation. And I leave it as an exercise to show that A cross B, if I take its component in x prime direction, it is equal to A cross B x component cosine of theta plus A cross B is y component sine of theta. Similarly, A cross B y prime component, if I am rotating, if I am changing only x prime and y prime axis and by rotation about the z axis, should be equal to minus A cross B the x component of sine theta plus A cross B y component cosine of theta. I leave this as an exercise for you. So, it is this combination A x b y minus b y a x and things like those that defines the vector product for us. So, product of two vectors one is a scalar product which is A written as A dot B, which is nothing but A x B x plus A y B y plus A z B z, and the other is the vector product which gives me a vector quantity which in a short term I can write as a determinant I j k A x A y A z B x B y B z, a determinant of this, and this is A cross B. I leave it for you to check that this gives the same expression as we used earlier.